Hi, I'm Kyle, and this is Fiberglass. You'll find this material everywhere, from obvious sources such as boats and cars, to not so obvious places like construction materials such as concrete and even electrical boxes. But what makes this material so versatile? And how do we get these thin, delicate glass fibers from a material that we know more commonly as sand? Check out my video and I'll show you how. This is my materials science presentation on fiberglass, but what is fiberglass exactly? Glass fiber, as its name suggests, is simply a long strand filament comprised of a glass. In this case, the glass is a non-crystalline silicate ceramic or an amorphous silicate. These strands are drawn into small threads, usually between 5 micrometers and 10 micrometers in diameter, and can be processed in various ways. Let's take a look at the history of glass before we get too much into that. The silicate that we'll be discussing is produced primarily from silicon oxide. Silicon oxide is abundant in the world in the form of sand. Silica has a very high melting point of 1700 degrees Celsius, and around 1500 BCE, sodium was mixed into this to reduce its melting point. Glass was introduced as an art and mostly decorative. Before humans synthesized glass, we found glass occurring in nature. This dark black glass, known as obsidian, forms when granite is melted by hot lava and recooled. This soda lime glass, as was discussed before, was first created in ancient times when Egyptian civilizations added sodium to decrease the melting point of the silicate sand. In 1664, a gentleman by the name of Ravenscroft developed this lead glass known as crystal, which is very shimmery and shiny, but has a very, very brittle characteristic. Later, in the 20th century, boron oxide was added to these silicates to create this borosilicate glass, which is very heat resistant, and you will recognize it from labs. Later, alumina was added to these borosilicates and created what is known as an aluminosilicate glass. This is even higher heat resistant and is very tough, and is used in chemical resistant bottles as well. Fiberglass was first commercially produced in the late 1930s. In 1938, the Owens Corning Corporation came out with a method of producing continuous strand filament fibers. Previous to this, fiberglass was mainly produced in this staple form and used as insulation in homes. The Owens Corning Corporation marketed theirs as fiberglass and the name stuck, and they were still one of the largest producers today. Today, fiberglass is used in construction materials like tiles and shingles and has over 40,000 applications alone as a reinforcement agent. It can be also combined with thermosetting plastics to form stiff, lightweight composites, as in the case of boats and automobiles. Modern glass is a combination of silicon oxide, calcium oxide, and other metal oxides such as sodium, boron, or aluminum. So glass is actually a state of solid matter. Many things can exist as a glass, and we'll notice that normally solids have this very ordered crystalline structure. A glass has this random ordered structure known as amorphous, which is due in part to the rapid cooling of a very viscous liquid to prevent these molecules from binding together into a crystalline structure in time. The addition of certain metal oxides can also produce cations that help this process. Borosilicate and aluminosilicate glass fibers are the two most commonly found today. Boron is added to create a very high heat resistance, and aluminum can be added to create an even higher heat resistance. These printed circuit boards use both in a combination that provides a very stiff, low-weight product, has great dielectric properties, and is very resistant to thermal expansion, which is great when it comes to production. Large corrosive-resistant pipes and tanks are lined with boron-free glass, which adds additional acid and corrosion protection. So we know kind of the basic ingredients of glass. Let's look a little bit more into what these ingredients do. There are three basic types of ingredient. There's a former, a flux, and a stabilizer. The former, in our case, most common is silica oxide. This produces most of the glass we know today. Other formers can be used, such as boron oxide or phosphorus oxide, but these glasses usually are water soluble. In addition to the silica, which has a very high melting point, we will add a flux, such as a soda oxide or sodium oxide, which lowers the melting point of this initial former, and they work together to create the network. In addition, a stabilizer is added in the addition or in the form of calcium, magnesia, or other metal oxides, and these release cations within the network of these formers that help to stabilize the compound as it cools and keeps it from forming crystals. Here we see a basic reaction in the sodium carbonate and a silicon oxide combining at a high heat to produce this soda glass, and it also releases CO2 from that carbonate. The sodium and aluminum joins the silicon oxygen network and act together as the main structure, whereas the calcium or magnesium and any other metal will enter the network usually as a modifier. These modifiers make the structure more complex, but are crucial in the retention of an amorphous structure as this viscous glass cools, preventing it from recrystallizing. We see here in the structure of a basic aluminosilicate glass that the silica and aluminum are forming the structure with oxygens bridging those, and then we have the calcium modifier cations, which serve as those stabilizers and keep that amorphous construction. Down here we see a simpler glass that just utilizes the silicon and the sodium carbonate. This is more commonly referred to as soda glass. Finally, we can see the basic crystal structure here of just a silicon oxide. Here we see a little bit of an overview of the fiberglass production process. We see once the product is heated in the furnace and sufficiently combined and melted, it is then transported via the forehearth into this forming area. The glass is extruded generally through a platinum and rhodium alloy bushing, where it is then water cooled and the polymer is applied usually to keep it bound together. These filaments can then be collected on a roll for further processing like weaving, or chopped right there on the floor and collected and bound together as mats or impregnated into polymer materials. Here I will talk about my favorite application of fiberglass, which is glass reinforced polymers and plastics. These are materials in which the fiberglass is combined with a thermosetting plastic, which creates this network, which is very structural. The fiber reinforces very directionally, so you'll see that when mats are comprised of multiple layers of fiberglass, that the directions between the different mats are angled, and these strands are aligned to provide maximum strength in all directions. Fiberglass is an ideal material because it has so many physical and chemical properties, including thermal and electrical insulative properties. It has a very high tensile strength. It has a very high ratio of surface area to weight, meaning we have large sheets that weigh very, very little. And it is incombustible as it is a mineral material. Here we will discuss the different types of fiberglass and their applications. The most basic is an alkali glass or A-glass fiber. It's very cost effective, very easy to make, and it can be used for most things, although A-glass is primarily used in jars and windows. The most common by far fiberglass we see in construction of all sorts of objects is E-glass. E-glass got its name from being known as electrical glass. It was used in electrical components early on. It has the same compound as the alkaline glass. It even has boron and aluminum, but it also adds certain concentrations of magnesium to increase its strength. It can be used in the aerospace industry, the marine industry, and many other applications. The other form of fiberglass I would like to discuss is some that you see pictured here in the top right, which is known as R or S glass. It is a trade-specific proprietary blend of different materials, usually magnesium, and altering the calcium and sodium levels of the glass to produce an even stronger, stiffer glass. Now we'll look at certain modern innovations that scientists have come up with using this fiberglass technology. First, we see that nanofibrous borate glass is used for treating skin ulcers and deep wounds. We also have bioactive phosphate glass fibers that help cells proliferate in an orderly and directional fashion and promotes bonding between implants and bone. We've also seen a rise in fiberglass reinforced composites in dentistry, which provides increased biomechanical performance. They can be repaired in the mouth and are biocompatible and non-toxic. Well, there's a bit of an overview of just the basics of fiberglass and all of its potential. I definitely learned a lot about the product, even more than I already did from previous experience, as well as some of the innovations that have come in recent years. Thank you so much for watching my video. You guys have a great day.